Hello, I am Ilias Cholis, and I'm going to talk about how we can use antimatter cosmic ray nuclei measurements in connection with dark matter searches in the Milky Way. And these are my relevant publications with my collaborators on this subject. I'm going to start with the measurement made by the alpha magnetic spectrometer, or AMS, on the antiproton to proton ratio, which is the published result is here. Focus only on the green data points. The x-axis is the rigidity, meaning the momentum over charge of these cosmic rays. And the y-axis, the green y-axis, is the actual flux ratio. You can see that the flux ratio is of the order of 10 to the minus 4. So basically, for every 10,000 protons of a given of the rigidities with this in this range, we observe only about 2 antiprotons. Now, where do these antiprotons come from? They are produced. These antiprotons are typically referred to as interstellar medium antiprotons, or secondary cosmic ray antiprotons, and they are produced when a cosmic ray primary, typically proton, has a hard inelastic collision with target material, typically also protons, in the interstellar medium. And if it carries enough of energy, it will produce cosmic ray antiprotons. So the question here is, could we have an additional contribution of cosmic ray antiprotons from, say, dark matter annihilations? When you have some dark matter particles, they annihilate to some combination of standard model particles, which then hadronize and decay, giving us, in the end, cosmic ray antiprotons. Now, this has been a subject that before AMS measurement was contested between different groups on whether we would be able to measure if dark matter is a thermal relic with mass such mass that it would produce antiprotons in these energies or rigidities, whether such a dark matter would give a detectable signal in cosmic ray antiprotons was a hard question before the AMS data. Now, after the AMS came about, there was a first paper by Cuoco, Kramer, and Crossmeyer in 2017 that suggested the presence of an antiproton, additional antiproton component that, if it is to be explained by dark matter particles, it would require some dark matter thermal relic particles with mass of the order of 50 to 100 GeV. Now, the fact that it's close, that it has that dark matter would need to have a cross section close to a thermal relic value is interesting by itself. There is an extra interest in that, though, in that specific mass range, since the same type of particles could explain the Fermi galactic center excess, which is an excess in gamma rays from the center of the galaxy that may also be explained by roughly thermal relic dark matter particles of roughly same order in mass. Now, why is the measurement of antiprotons and connecting them to dark matter a challenging subject? That has to do with the actual uncertainties, the uncertainties on the antiproton background, meaning the antiproton that comes from the inelastic collision in the interstellar medium. Now, the uncertainties are associated with three things. First, the uncertainties on the antiproton production cross-section from those inelastic collisions. Second, with the propagation of cosmic rays in the interstellar medium. So what are the conditions in the interstellar medium in general? And third, with the propagation of cosmic rays through the heliosphere. The heliosphere is a volume of space that is affected by the solar magnetic field and the solar wind. It extends out to at least 100 AU, and its effect on the cosmic ray spectra is known as solar modulation. I'm going to go over how we handled with my collaborators these three uncertainties. So regarding the antiproton production uncertainties, these are large mainly because we rely on experiments from the 70s, where we had, again, we didn't have colliders. We had basically a beam of particles hitting a fixed target. And since we had mostly old data, we have even our parametrizations were from 80s and 2000s, but they were relatively old. So since then, there has been some advancement in connection with some more recent measurements, but also there has been a work by DiMauro et al. That showed that quantified the level of uncertainties directly for the part that has to do with the proton-proton collisions. So on this axis, this plot, the x-axis is the kinetic energy of the cosmic ray proton, and on the y-axis is the level of uncertainty from a given choice, a given parameterization on the cross-section. So the cross-sectional uncertainties on the proton-proton collisions giving directly antiprotons are at the level of several tenths of percent at low energies, meaning GeV in kinetic energy, up to, and even up to 50% at the TeV scale. Now, in addition to those uncertainties, one has to include the fact that while in experiments at lab you observe antiprotons and your antineutrons are not going to decay, in the interstellar medium antineutrons are going to decay. So you have to include those and the contribution of antiprotons from the antineutron decay in the interstellar medium. In addition, you have to include the fact that collisions that can also give antiprotons include heavier nuclei. And the collisions including heavier nuclei, mainly helium, can be responsible for about 40% of the observed antiproton cosmic rays. Regarding the interstellar medium propagation uncertainties, what we do is we use Galprop numerical solver, which is developed by Moskalenko, Strong, and others. And that solver, that package, basically takes the propagation equation of cosmic rays, where you study the cosmic ray density at given position, time, and at given energy throughout the Milky Way. And you calculate that based on what the sources are, what the distribution of cosmic ray sources in the Milky Way, and how those cosmic rays, once injected into the interstellar medium, diffuse, go through diffusive reacceleration, which is diffusion in momentum space, and convection. For other type of cosmic rays, there are also energy losses. For protons and antiprotons, these are the main physical effects. So what we do is we build models, several different models, making different assumptions on the physics of the sources and the propagation of cosmic rays, and then test them with several cosmic ray measurements from Pamela, which is the predecessor of AMS measurements, and also since 2000, and also Voyager 1. Voyager 1 is important because since 2012, it has entered the local interstellar medium, so it has given us measurements of what's the true local ISM spectrum here of cosmic rays, here shown for cosmic ray protons, without the effects of solar modulation. Finally, we also have to deal with the solar modulation uncertainties, which are large at low energies. And there we have to deal with the fact that we know from simulations that cosmic rays of different charges propagate from outside, from the interstellar medium volume, inside through the heliosphere and into the Earth, or the location of the Earth, following very different paths. We also have to include the fact that as they are propagating from outside in, where our detectors are, they do go through diffusion, which is though highly anisotropic, and there are also drift effects. Finally, we have to take into consideration energy-dependent effects and time-dependent effects, since the magnetic field and the solar wind do change with time. To handle all those uncertainties, though, what we rely on is we use the fact that since AMS is a very sensitive experiment, it has also provided us with the proton, especially proton and other cosmic rays measurements performed at different monthly intervals. So here, for instance, I show you the measurements from AMS from 2011 to end of 2012 for cosmic ray hydrogen and how that evolves with time and for specific energy ranges or rigidity ranges here. So basically, we rely on those monthly data and very refined measurements on the monthly data to constrain the properties of solar modulation. Combining everything together and going back to the antiproton to proton ratio spectrum, this is kinetic energy of protons and antiprotons. This is again the data points from AMS. This band, the line refers to a very specific, the solid line, the black solid line refers to very specific choices. The important thing here is the bands. So the impact of solar modulation is shown in green. You see that solar modulation is still relevant at energies of about a few GeV and below. The assumptions, the uncertainties relating to the assumptions on the remaining uncertainties relating to the assumptions on the interstellar medium physics and the injection properties of cosmic rays from their sources are depicted in this light blue color. This is important throughout the energy range, but never dominant. And it's always around 20% or so. And then the orange band is the uncertainties relating to the the uncertainties on the antiproton to proton ratio originating from the uncertainties on the antiproton production from proton-proton collisions. So after including all those effects and combining all those effects into the red band, we find that there are still two regions of interest in the spectrum. One at the very high end, which we think may be related to supernova physics, and another one for antiprotons of energy around 10 GeV. A different way of showing that is you take the secondary ISM antiproton component, and then you allow for a second component of dark matter origin. Now, to model properly that dark matter component, you need to make specific choices of the interstellar medium. So I saw here for one specific choice, results for one specific choice of interstellar medium. We go over different choices of interstellar medium models. And then once you fix the interstellar medium, you have to fix the properties of the dark matter particles, meaning their mass, their cross sections. Here I saw cross section times the velocity, where velocity here is the relative velocity of dark matter particles in the Milky Way, and also the annihilation channel. So that here I'm assuming that, for instance, this specific point would refer to a dark matter particle of 100 GeV with a cross section of something like 10 to the minus 26 in units of centimeter cubed per second, and annihilating entirely to BB bar quarks. So you allow for, and you take many, many different choices in that parameter space and test each one of them. So choices in that dark matter parameter space that are above the black line are excluded at the 2 sigma limit. The black line is the 2 sigma limit on performing a fit of an additional component on the antiproton to proton ratio. Choices, points below that actually are allowed within the 2 sigma, and regions around these blue bands are in those two specific regions, there is a preference for a dark matter, an additional dark matter component that is more than 3 sigma. It was a similar result to our result in 2019 from Cuoco et al., practically within the same week, roughly in the same week. Now we can, and like I said, now the high-end part of it is related, or the high mass part of it could be actually explained by supernova, but this range is, first of all, in agreement with a rough estimate of the thermal relic for dark matter particles to BB bar quarks, and also is in agreement to the gamma ray galactic center excess. To give you another idea how significant that excess of antiprotons is, at its peak, roughly, which happens at around 10 GeV. So at roughly 10 GeV, 1/10 of the observed antiprotons originates from dark matter. So that's a significant component. Now, what's next? Well, we can also talk about heavier nuclei, antimatter nuclei. For the record, AMS has made some unofficial claims of anti-helium cosmic ray events. So we may actually have some detection of that already. Now, how do this antinuclei get to be produced? These more massive antinuclei get to be produced in the interstellar medium through the same type of processes that produce antiprotons. Here I saw the example of an antideutron. You basically, again, have some primary high energy cosmic ray proton having a hard inelastic collision, coming with such enough of energy as to produce both an antiproton and an antineutron, which can then coalesce, merging into an antideutron. In order for them to coalesce, their relative momentum difference has to be smaller than some value, P0, which we refer to as coalescence momentum. The exact value of that P0 is not very well measured, and it's a major source of uncertainty. Basically, when it comes to this heavier antinuclei, we repeat the same process. We here saw the example for antideutrons and the spectrum of antideutrons and how that depends, how its measurement is sensitive to the various type of uncertainties for solar modulation, for injection propagation through the interstellar medium, and also for the production cross-section uncertainties and the exact choices we make on the coalescence momentum. And we can repeat that for multiple particles. Here I saw the total, the spectra from in the solid lines and bands secondary interstellar medium fluxes for antiprotons, for antideutrons, for antihelium-3 and antihelium-4. Focus on the bands. So one thing you notice is as you go as you add every single nucleon into this anti-nuclei, the flux of those secondary fluxes is significantly suppressed by several orders of magnitude. And the bands, the uncertainty of those fluxes becomes enormous and becomes very large exactly because, predominantly because of the particle physics uncertainties, the uncertainties relating to the proton-proton collision, cross-section, and the coalescence momentum. However, a thermal relic dark matter particle that can possibly explain the antiproton excess and is responsible for, it can give you of the order of a 10% addition in spectra of, antiproton spectra. When it comes to antideutrons, antihelium and antihelium-3 and 4, it can have a dominant contribution at low energies that is well above even the uncertainties, the very large uncertainties on the secondary fluxes. Moreover, we have found that effects like diffusive reacceleration in regions of high turbulence can reshape the antimatter spectra in such a way as to move them from energies where they wouldn't be sensitive, where AMS and GAPS wouldn't be able to detect them, into energies where you can have a measurement of such events from AMS and GAPS. There's also a complementarity between the AMS and GAPS, future GAPS experiments. And in fact, by comparing different anti-deuteron measurement numbers, we would be able to learn both properties about the dark matter and even some interstellar medium properties, interstellar medium physics. And I'm going to conclude by combining all searches together, again, in this parameter space where of mass versus cross-section, for a dark matter particle, assuming this dark matter particle goes directly to BB bar. This part of the parameter space is excluded by CMB limits. This part of the parameter space is excluded by dwarf spheroidal limits from observations in gamma rays towards close by dwarf spheroidal galaxies. The black solid line is the 2 sigma limit from antiprotons for a combination of different ISM assumptions. And the red band here, which is the red blob, is the galactic center axis. So this is a positive axis. These are limits. This is an actual axis. The green blob is the antiproton axis that I mentioned before. You can see that for some choices, the two are actually can be agree. Moreover, they agree also with a thermal relic. They agree with a cross section for a thermal relic particle that annihilates entirely to BB bar. Finally, if those two axes are to be in agreement with each other and to be originating from dark matter, then you should expect to see some anti-helium events and several anti-deuterium events. That can be seen here by, I've made some for specific choices. I've plotted how many, for what combination of dark matter versus cross-section choices would give us one anti-deuterium, one anti-helium event, anti-helium-3 event, and one anti-deuterium event. Thank you.